Hey folks, and welcome back. We're going to be taking a look at electromagnetic waves today. This is our final topic for our waves unit, and it's going to be our final set of notes for this entire school year. So let's make sure we got that Cami doc open, and let's get rolling. Now let's just remember real quick that waves are energy being carried from one place to another, and there are two main types of waves. We talked about mechanical waves, and those were kind of all the waves we've been talking about for the last couple classes. Remember that they require matter to travel through. And so today we're going to be talking about the other major type of wave, which are electromagnetic waves. So what exactly are electromagnetic waves? Well, these are transverse waves that are consisting of both an electric and a magnetic field. So that's why they're called electromagnetic waves. Now, we're not going to get into the specifics of all of that, but the upshot of the fact that it is made up of electric and magnetic fields is that electromagnetic waves can travel through empty space or through matter. So electromagnetic waves don't require matter to be able to move through like we saw with mechanical waves. And so electromagnetic waves are able to travel from the sun to the earth, right, which is across space where there isn't any matter, which is a distance of 93 million miles. So that's obviously quite a distance without having any matter to be able to move through. How fast do those electromagnetic waves travel? Well, electromagnetic waves travel at 300 million meters per second. Yes, 300 million meters per second. Now, that is an actual speed, right? It's not just instantaneous. It feels instantaneous here on Earth, right? Because the distance is so short. When you flick on a light switch, right, you see the light immediately, or it feels like it's immediate, and that's because you're so close. But over very big distances, and remember, we just said that Earth to the sun is 93 million miles, it does take time for electromagnetic waves to travel. And so if you were to measure the electromagnetic waves traveling from the Earth to the moon, it would take 1.3 light seconds, or basically 1.3 seconds for that light to arrive from the moon. From the Earth to the sun, it takes 8 minutes for those electromagnetic waves to arrive, and light is an electromagnetic wave. Or from the Earth to Mars, it takes almost 13 minutes. So that means that when you are looking at the sun, or when you're seeing light from the sun, you shouldn't really ever be staring directly at the sun. You are actually looking at the sun as it was 8 minutes ago. When you look at something that is very far away, the light that is reaching your eyes, it actually takes time for it to get there. So you're actually looking into the past. So when you look out and you see stars at night, you are literally seeing those stars as they were in the past, but the light is just now reaching your eyes. So pretty wild thing to think about for sure, but an interesting consequence of the fact that light does travel, electromagnetic waves travel at a certain speed. So what exactly is the electromagnetic spectrum? Well, the full electromagnetic spectrum is all of the different waves that exist with different frequencies and wavelengths. And we've kind of arbitrarily chopped them up into some different categories, okay? So basically we have 7 different types of electromagnetic waves. We have radio waves, microwaves, infrared waves, visible waves, ultraviolet, X-ray, and then gamma rays. And each of those different types of electromagnetic waves have some slightly different properties, and we use them for different things. Now, what you'll notice is that they are categorized based on their wavelength. Okay, so you'll notice that the wavelength starts big, right? This is 100, and this would be in meters. I'm sorry, this would be 1,000 meters. So radio waves can be very, very big, right? The wavelength can be very big. If you get down here to the gamma rays, right, you'll notice that the wavelength is very, very short. And remember that this is going to be the opposite for the frequency, right? We have a lower frequency over here for radio waves, and we have a high frequency over here for gamma rays. And you can kind of see that here, right? You can see how the frequency and the wavelength are changing with the different types of electromagnetic waves. But basically, those are the 7 different types of electromagnetic waves. Visible, this is visible light. This is what we can actually see. So all of what we can actually perceive with our eyes exists within this visible spectrum. right, which is actually a fairly narrow band of the entire electromagnetic spectrum. So how does the frequency and the wavelength of electromagnetic waves relate? Well, because they all travel at the same speed, that 300 million meters per second, the frequency and the wavelength are inversely proportional. And you maybe want to know why that is, right? Well, remember that the speed of a wave is equal to the wavelength times the frequency. All right, and the reason, so therefore, because the speed is staying constant, because it's not changing, as the wavelength goes up, the frequency must go down. And the opposite is true, right? If the frequency goes up, the wavelength is going to be going down. And that's just because we're holding the speed to be constant. So they are inversely proportional or inversely related, which we've talked about before with other things as well. So again, in this picture, we can see a little bit more clearly just how small the visible light spectrum, what we can actually perceive, is compared to the entirety of the electromagnetic spectrum. And again, we can see that when we have long wavelengths over here with radio waves, we have a low frequency. And when we have short wavelengths over here with gamma rays, we have a high frequency. So again, that is the inversely related nature of this. Which electromagnetic waves are the highest energy? Well, gamma rays over here have the most energy. And you can see right here that the energy is increasing as the frequency is increasing. So the higher the frequency, the more energy that the waves have. And that makes sense if you think about kind of like, what are these things used for, right? Well, X-rays, you used to be able to see through things, whereas like microwaves you use to heat up food. Right? There's a little bit of difference there in terms of like what they're being used for, and that's because of the energy that they have. All right, last thing. Why do objects look a certain color? Why is it that my shirt is green, right? Or why is it that this car is red? Well, sunlight, right, with the light that comes from the sun, also called white light, so light that comes from lights as well, like light bulbs, things like that. Those are also often considered white lights. White light contains all of the visible light spectrum. So when you have all of the colors together, it appears white. So the whiteboard behind me, right, it looks white because it is reflecting all of the colors of the visible light spectrum. Let me get myself out of the way. Yeah, it's reflecting all of these colors. And so when your eyes see all of the colors, they perceive it as white. Black is the absence of all the colors. So the bottom here of the screen, right, it appears black because it is absorbing all the colors, and so therefore it's not reflecting any of them, and so your eyes see the absence of visible light waves as black. So why does something appear red? Well, something appears red because it is reflecting the red part of the visible light spectrum, and it is absorbing all of the rest of it. Okay, so something appears red because all of these waves are hitting it. The pigments that are inside this paint, right, they are absorbing the yellows, the greens, the blues, the purples, right, and then it is reflecting the red. My shirt appears green because it is it is reflecting the green, and it is absorbing all of the other colors, and so it appears green. And so that's the reason why things appear a certain color, is because it is reflecting the color waves that match up with this. Or it is reflecting the color waves, the waves that are that color. All right, folks, so that's it for notes. You've got a summary of the notes, and then we want to learn a little bit more about these different types of electromagnetic waves. So for your practice, you're going to go to a website. The link is at the top of that page. You're going to be learning a little bit more about kind of how are those waves made, what are some of the uses, and what are some of the dangers. So make sure that you fill out that information, submit the assignment, and then that is your last graded assignment for this school year, other than our quiz on waves, which is going to be next week. All right. Hope you have a wonderful rest of your day. If you have questions or need anything, please let me know.